Hey guys, this is part one of the series on physics-informed neural networks or PINNs. Imagine collecting a single data point costs you an afternoon in the lab or costs thousands of dollars. Or maybe like large language models, you have consumed all the useful data and nothing is left to scale up the model. In that case, how would you train a neural network that conventionally needs a gigantic dataset? Feeding big data to a neural network is not the only way to train it. Alternatively, we can feed the laws of the system of interest into the neural network and train it even more accurately. That is the subject of physics-informed neural network, but don't let the name misguide you. PINNs can actually be used to solve common machine learning problems as well as solve physics equations. For example, we can train a PINN to predict house prices or the financial market. I will get to this in a future series of this course, but in this video, I will show you how we can solve differential equations using neural networks. We will start with the heat on a piece of metal, get to the equations that governs it, and then solve the equation two different ways. First, with a regular neural network, and then with a physics-informed one. So let's assume this image shows the temperature of the surface of a piece of metal. Here, x and y are the physical coordinates of the metal, as shown in the image, and the temperature U is represented by the color bar. So the color shows the temperature over the surface. Purple is the coldest temperature, and dark red is the hottest. At the very beginning, we start heating the left and right sides. That is why both sides are red. But the rest of the surface is at the coldest temperature possible, shown by the purple color. Now, since there is a temperature difference across the surface, heat starts to spread out. The equation that explains the time evolution of this temperature is the famous diffusion equation, which says the partial derivative of u with respect to time equals alpha, which is a constant, times the sum of the second derivative of u with respect to x and the second derivative of u with respect to y. And yes, you heard it right. This is the same equation underneath advanced AI image generators, the diffusion models. Here you can see an animation of how the temperature evolves over time and spreads throughout the surface of the metal, according to this equation. Now, if we wait for a relatively long time, the temperature reaches a steady state, after which it stays still for as long as we keep the boundaries at the same temperature. This image shows that a steady state temperature distribution across the metal. At this point, the time derivative in the diffusion equation becomes zero since the temperature is no longer evolving, and the diffusion equation reduces to the so-called Laplace equation. The second derivative of u with respect to x plus the second derivative of u with respect to y equals 0. Now, the question is, how do I solve this differential equation or any other more complicated one using neural networks? This is what we call a direct problem. In this notebook, we will use PINNs to solve the Laplace equation above, given the boundary conditions. Okay, so let's first clearly state the problem. We have a metal that is absolutely cold. We take two heaters, place them on both sides of the metal, and keep the heaters' temperatures fixed at all times. And since our heaters have their own thermometers, we know the temperature at the x equal -1 and x equal 1 sides of the metal. We also know that if we wait a few minutes, the temperature across the metal becomes stationary and is governed by the Laplace equation. So the question is, what is the solution u of x and y to this equation? In other words, we want to train a neural net to tell us the temperature for any pair of x and y so that we can make this plot of the steady state of the temperature of the metal. So we start with a neural network whose input layer has two neurons, one taking the value of x and the other taking the value of y, and the output layer has only one neuron, whose value is the temperature u. The neural network is now a function that performs the transformation from the pair x and y to u, with the hidden layers represented by the arrow. The number of hidden layers and the number of neurons in each is, to some extent, arbitrary. We just need enough free parameters to perform the right transformation, but not so many that the network overfits. So we work with 5 hidden layers, each having 20 neurons, activated using the tangent hyperbolic or tanh function. In the following cell, we implement this network in PyTorch. It takes the two inputs, passes them through the 5 tanh layers, and returns a single output. In total, the network ends up with 1,761 parameters. Now, up to this point, we have a rank transformation from x and y to u, because the network is not trained yet, and its three parameters just have some unadjusted initial values. Just to check that we have a transformation at all, we compute the rank value of the heat U at x equals 0.1 and y equals 0.2, and it returns something like minus 0.0996. It is meaningless for now, but at least it confirms the network is working. To see the difference between PINNs and conventional neural nets, let's first train this network the conventional way. What I mean is, let's train it without physics, just using data and no physics domain knowledge. So first, we need to collect some data. For that, we need to get into our lab, take a thermometer, measure the temperature at some random x and y places across the surface of the metal. This plot shows the random places where we used our thermometer and measured the temperature. As you can see, we have data points both on the boundary of the metal and throughout its surface. In the following cell, we import that collected data into a data frame so we can use it for training a regular neural network. Now that we have the network and the data, we need to define the loss function to minimize and train the model. We use the conventional mean squared error over the data points, that is the average of the squared difference between the network's prediction and the measured temperature, where n is the number of rows in the dataset. And we implement this loss in PyTorch. Now let's minimize the loss to find the optimal values of the three parameters. In the following cell, we use gradient descent in PyTorch, specifically the Adam optimizer, to train the model for 62,000 epochs. As the training goes on, you can see the loss dropping lower and lower until it becomes tiny, and we plot the loss against the epochs on a log scale to watch it go down. To evaluate the performance of our model, let's use it to predict the temperature on a dense grid covering the whole domain of x and y pairs, and compare with the exact temperature values, which are given by u equals x squared minus y squared. Now you might ask, if we already know the exact solution, why bother solving it with neural nets? The answer is that we rarely know the exact solution of differential equations, but we can solve almost all of them using neural nets in the same way we are doing in this course. Okay, back to the comparison. The standard metric here is the root mean squared, or RMSE, which is the square root of the average squared difference between the neural net's prediction and the exact solution, summed over all the rows. And for reasons I'll discuss later in the course, we'll also split this error into boundary points versus interior points. In the code, we implement the RMSE, create a dense grid of x and y pairs, predict the temperature with the network, then use the exact solution to find the true temperature at the same locations and compare. When we print them out, the overall RMSE for the regular net is about 5 times 10 to negative minus 4, and it's roughly the same on the boundary and in the interior. But RMSE just gives us a single number. So let's see how the errors are distributed across the surface of the metal. For that, we plot the absolute value of the difference between the predicted and true temperatures. In this plot, white means low error and dark blue means high error. Now that we have a regular neural network capable of predicting temperatures on the surface of the metal, let's move on to the next subject, using physics to train a neural network, the so-called physics-informed neural networks. Interestingly, we are going to use the exact same network structure as before, the same input, hidden and output layers, and the same neurons. The inputs are still x and y, and the output is still the temperature u. Now, if you ask what is different, the answer is how we train the network. For physics-informed neural networks, we have two loss functions, one for points on the boundary, which we call the training set, and the other for points inside the surface, are called the collocation points. The collocation points have one main difference compared to a regular dataset. We no longer need to measure the temperature for them, and that is a game changer, because collecting data is not always viable. Some experiments are very expensive, and sometimes we have already used all the useful data. For the metal in this course, it means we only need to go to the lab and measure the temperature on the boundary. That is a significant reduction in the number of measurements we need to make. Now, let's discuss the loss function we need to minimize to train the PINN. The complete loss is actually the weighted sum of two loss functions, one for the boundary and one for the interior of the surface. The two weights, omega, are constants that decide which loss should be more important, and most of the time, we can just set them both equal to 1. The data loss is defined just like in conventional neural networks. One common choice is the mean squared error we used above. The only difference here is that data points are only on the boundaries to enforce the boundary conditions. We implement this in PyTorch using the same dataset as before, but filtering out every point that is not on the boundary. We plot those boundary points, then convert the x and y and temperature columns into tensors and define the data loss. Now, let's get to the second term in the loss function. It deals with data points from the interior of the metal and ensures the physics law is enforced there. In other words, this loss comes from the differential equation itself. First, we need to define the residual. That simply means we bring whatever is on the right-hand side of the equation to the left side, so the right-hand side becomes 0. For example, if we were dealing with the Poisson equation, where the second derivatives of u add up to some function rho, the residual would be the second derivative of u minus rho. In our case, the governing equation is Laplace, whose right-hand side is already 0. So the residual is just the second derivative of u with respect to x plus the second derivative of u with respect to y. Now that the residual is set, we define the PDE loss as the residual squared averaged over some random collection of points from the interior of the domain. And it is important to note that we are using the neural network's prediction of the temperature in this equation. The advantage is that we don't need the true temperature values at these points for training. We can just randomly pick a few x and y pairs, insert them into the sum, and that's it. By minimizing this physics-based loss, we force the equation to balance out to 0 at these locations, and the network learns the underlying physical laws. Now comes another question. We already know how to use the network to compute the temperature at a given location, but the loss function takes derivatives of the temperature. So how do we find the second derivative of u with respect to x and second derivative of u with respect to y? That is where automatic differentiation comes in. If you don't know how the method works, I've covered it in another course. For now, just keep in mind that it is a method to take derivatives of the output layer of the network with respect to its input layers. In our case, derivatives of the temperature with respect to x and y. And fortunately, these are all implemented in PyTorch, so you can already use them even if you don't yet know how they work. Let me emphasize how important it is to actually learn how these methods work. It is true that you can use PyTorch to take these derivatives or whatever else is possible, but in that case, you'll only be able to solve problems that are already solved. And that means coding agents like Cloud Cowork or OpenAI Codex can do it better than you. And that work is already replaced. So if you don't know automatic differentiation, add it to your to-be-learned list and let's move on. Now, let's get into the implementation. In the following cell, we define the residual for the Laplace equation and raise it to the power 2, which gives the term in front of the sum in the loss function. Note that we use the grad function twice to differentiate the network output with respect to its inputs, and we set create graph equal to true so that these derivatives can themselves be differentiated during the training. We also need to import the collocation points, which are random data points from the interior. For now, we again use the same dataset as before, but throw out the boundary points, and we also delete the temperature column, as if we didn't measure it in the first place. We import the data and plot it. And notice that these rows have no true value for the temperature. That is the characteristic of collocation points. We plot them just to make sure there is no data point on the boundary. And now we use the residual to implement the PDE loss. We convert the columns of the data frame into torch tensors and insert them into the residual squared function we defined above. And now comes the training part. We already have both pieces of the loss, the data loss from the boundary points and the PDE loss from the collocation points. We just add them together to get the total loss, and just like we did for the regular network, we use the Adam optimizer to repeatedly tune the free parameters of the network so that this total loss gets smaller and smaller. In the following cell, we run this optimization loop for 62,000 epochs and keep track of how the loss decreases. We then plot the total loss on a log scale, and we also plot the two losses separately so we can see whether the network struggles more with matching the boundary data or with satisfying the PDE. Now that the PIN is trained, let's evaluate it exactly the same way we evaluated the regular network. We predict the temperature on the same dense grid covering the whole domain and compare against the exact solution x squared minus y squared using the same RMSE function and the same boundary and interior split. And here are the results. The overall RMSE for the PIN is about 1 times 10 to negative 4, which is a lot smaller than the regular networks. Here is a side-by-side comparison of the two. As you can see, the PIN's RMSE is smaller than the regular networks on every single metric, even though it never saw a single true temperature label in the interior of the metal. Let's also plot the absolute value of the difference between the predicted and true temperatures across the surface, just like we did for regular network. Again, white means low error and dark blue means high error. And notice how much lighter this map is compared to the regular network's error map. That is the 3 to 4 times lower RMSE showing up spatially. And here is the reference that I used for this video. Check it out if you want to dig deeper. So with this, I conclude part 1 of the PINS series. The takeaway message is, with PINS, you can train a neural network with less data, which is more accurate than a regular neural network that needs much more data to train. Something that I did not explicitly demonstrate in this video and that I leave as an exercise is the other advantage of PINs. Unlike regular neural networks, they can predict domains beyond their training data because they have learned the physics of the system. And here is a question for you before the next part. Remember, I asked earlier whether we could train a PIN to predict something like house prices. Think about what the physics laws would even mean for a problem like that, and write your answers in the comments below. And please send this video to someone who might find it useful. Your word of mouth is the best way to support me in creating more videos like this. And finally, I run a mentorship program where I can help you apply these models in your own projects. If you are interested, use the link in the description below to book a short call.